Welcome back, Pre-Calc. We are continuing on with mathematical induction, and I don't want to skip any problems because I picked all of these out for a reason. I thought they were all good, but I might move a little bit quicker. So if you feel like just putting the pencil down and following along, that's fine. Notice that sometimes they don't use the same notation, the same words, but positive integers is just a fancy way of saying that the first integer that's positive is 1. So we're still starting with n equals 1. I just want to point that out, that we don't always use the same lingo. But in this statement, it's just saying, okay, is it true that 1, if n is 1, is less than 2 to the first power? Well, 2 to the first power is equal to 2. So yeah, the base case is true. But now what we need to do is the inductive step. So in our inductive step, we are still doing n equals k plus 1. Now just so you know, we still know that n is smaller than 2 to the n power. So in this case, I know it's not in the same form as the previous problems, but I'm still replacing n with k plus 1 is less than 2 to the k plus 1 power. This is what we want to show. And how can we show that this is still true? Well, I can't really do anything with this k plus 1. I might point out something about that here in a second. But I do know that this 2 to the k plus 1 is equal to 2 to the k times 2 to the first. Because remember, if you're multiplying with the same base, you add those exponents. So what we need to establish is this statement somehow. So these two things are equal and these two things are equal. And we already know that 2 to the k is bigger than k. So since, I'll write it this way, k is smaller than 2 to the k, it follows, and I don't know how obvious this is to you, but it follows that adding 1 to k is not going to be bigger than multiplying this number by 2. So k plus 1 is going to be smaller than 2 to the k times 2. And I'll give you the notation that math people use for therefore. It's just 3 dots. Therefore, k plus 1 must be smaller than 2 to the k plus 1. So the entire premise of mathematical induction is that you're setting up these dominoes and you use that domino to prove the next step. I know if the domino analogy is not making a whole lot of sense, this might be a struggle to explain, but I want you to pay close attention to the next one because this is the type of problem that I stuck on the test. So this is more of a test-like problem. So you might want to completely understand this. Okay, so I think I'm ready for this. So again, mathematical induction, we have to do the base case. And by the way, somebody pointed out, I actually have a typo here because the upside down A actually stands for all. So I accidentally wrote out for all, but this is the same thing as n is a positive integer. You've seen this z before. You may not have seen this e before. It says n is an element. That's what that e stands for. Of positive is an element of positive integers. That's what that plus sign means at the end. So I know I'm throwing a lot at you with new notation, and that might be scary, but I think you guys can handle this. So let's start with the base case. The very first positive integer is n equals 1. So if I plug in 4 to the first power, just plugging in n is 1 minus 1, okay, well I get 4 minus 1, which is 3. And all I need you to say is something along the lines of, since 3 divides 3, that's what it means to be a factor. I don't know if I have to explain that. Since 3 divides 3, the base case is true. And now I need to prove this for the inductive step. So the inductive step is for n equals k plus 1. And somehow I need to use this fact up here again. So let's talk about what's happening. So all I know is that 4 to the n minus 1 is divisible by 3. We've established that in the base case. So let's look at the next piece, the next term. Well, 4 to the k plus 1 minus 1, well, that's equal to 4 to the k times 4 to the first minus 1. I hope you agree with that, because multiplying with the same base, you're going to add those exponents together. So the next thing, it might seem weird, but stick with me, I think it makes sense, is I can factor out that 4 in this piece, and I'm going to leave it as 4 to the k. I'm going to leave it as minus 1. So what I'm actually doing is I'm subtracting 4 in this problem. And that's only okay if I add 4 later. And let me explain a little bit more. So if I distribute this 4 times 4 to the k, I get this piece. Well, 4 times negative 1 is negative 4, which is not up here. So I'm fixing that by putting a plus 4. So minus 4 plus 4, I'm really adding nothing to it. And I'm just going to move this minus 1 over here. So you might be looking at me or looking at this work and saying, well, why on earth would you do that? Well, in this first piece, I'm going to leave that alone now. But 4 minus 1 is equal to 3. And so here's the real lesson here, is this piece divides 3. We proved that in the base case. And this piece is divided by 3. I guess I wrote this wrong. 3 divides that piece, but divided by 3. And 3 can be divided by 3. And I hope all of you would agree, maybe I need to explain a little bit more, but if this number is divided by 3 and this number is divided by 3, then adding them together will still be divided by 3. I could think of several examples of 2 numbers that are divided by 3, and then if I add them together, can still be divided by 3. So for the sake of ease and the sake of writing, because I know I'm already really long into these videos, I'm just going to put a box right here and say that that the inductive step is true, that we have shown enough work to get that this is divisible by 3. In the review, I have another problem that's very test-like, where I'm asking you, and the reason why I'm saying it's test-like is because it's a factor problem. But because this video is already super long, I'm going to stick to what I said. I'm going to skip this problem. I'll have you skip the problem in the homework as well as like this one. Just a different year, maybe I would still teach it. But I have one more thing that I need to teach because it is on the test as well. Just as a heads up, before calculators, students had to memorize these formulas. So be grateful that I've only gone through 2 of these examples and I didn't make you prove all of these. So different years, you might have some other things. And then this last problem is also a test-like problem. Test-like. And I have enough time to finish this and my explanation. But if you notice in the problem, the reason why this is a quadratic model, and I tell you it's a quadratic model on the test, is because when you look at the difference from one number to the next, it goes by 2, by 3, by 4, by 5, by 6. None of those numbers are the same. But if I look at the difference, the second difference, the difference of the difference, they're each going up by 1. That is your indicator that it's a quadratic model. So how do we solve this? I've been using this notation, so y subscript n. You're probably used to ax squared plus bx plus c. Well, I switched over to n because it's the nth term. for each one of them instead of x. So starting with the first term being 3, what I'm doing is I'm replacing the n's in the problem with 1. Well, 1 squared, because it's the first term, so n equals 1. That should be fresh in your mind. Well, 1 squared is 1, so it's a. 1 times b is b, plus c. And then go to the second term, which is n equals 5. Sorry, the y value is 5, but n is 2. So 2 squared is 4a. N is 2, so 2b plus c. And then the third term is 8. But again, n is 3 for the third term, so 3 squared is 9. 3b. And once you do a few of these problems, you'll notice, I think you'll notice, all of the work is the same. And it's actually fastest if you just do the top piece and you negate everything. You probably remember problems similar to this in Algebra 2. So what I can do is I can combine the top two equations because the c's will eliminate. Negative 3 plus 5 is 2. Negative 1 plus 4a is 3a. Negative 1b plus 2b is 1b. And I can also combine the top with the bottom equation. Negative 3 plus 5 is, I said that wrong, negative 3 plus 8 is 5. Negative 1a plus 9a is 8a. Negative 1 plus 3b is 2b. And probably what I would do next is just what I would do is I'd multiply the top equation by negative 2. Negative 4 equals negative 6a minus 2b. So you can see the b's would eliminate, and I get negative 1. That's positive 1 when I add those together. I'm struggling right now. I don't know why. And so a must equal 1/2. So once you have your a equals 1/2, you can go up here and you can solve the equation now. So 3/2 plus b, and when you subtract 3/2 over, you get b equals 1/2 as well. And now I can go to, I would probably just go to this top equation, plugging in b here. I guess I need a 1/2 and a 1/2. So I would have 3 is equal to 1/2 plus 1/2 plus c. So then c must be equal to 2. 1/2 plus 1/2 is 1, subtracted over. So the equation I just came up with, I'm going to call it y sub n still, is 1/2 n squared plus 1/2 n. I'm replacing my a, my b, and my c now in this problem. And I'm not confident in this answer because there's a lot of fractions going on here. So I'm going to pull up a graphing calculator just to see. And I'm going to go to y equals, you're probably used to these formulas from chapter 8. I'm just going to type it in using x, so, whoops, 0.5x plus 2. And I'm just going to go to my table and see if I get the same y values I should have. 2, 3, 5, 8, 12. 2, 3, I must have done something wrong. No, I didn't do anything wrong because I started at n equals 1. So it was 3, 5, 8, 12, 17, 23. 3, 5, 8, 12, 17, 23. You might have heard my confusion because sometimes people will start with n equals 0. I don't know why I thought that. I've already worked through 3 of these problems. And then I thought I did this one wrong. But this video is already super long. You're 3 videos long. As I mentioned, I already worked through the homework, but you should be ready for it at this point. And you can skip, where did I have? You can skip number 4. This is the problem that I skipped in the notes. But everything else I think is pretty good. And we're at the point in pre-calculus that the math should be pretty difficult. So it's not extra credit. I went ahead and worked through it if anybody's interested in seeing it, but you do not have to do that for your work.